Theoretical physics is caught in a standoff. On one side, general relativity models the universe as a smooth, continuous geometry. On the other, quantum mechanics describes a reality built from discrete, probabilistic states. Einstein's field equations offer incredibly precise predictions for gravitational mechanics at macroscopic scales, but these equations inevitably succumb to mathematical breakdown when confronted with regions of extreme density. Look at the primordial Big Bang, or the interior of a black hole, and the math yields infinities. The predictive power of the continuous metric tensor completely collapses. This mathematical failure suggests that the four-dimensional spacetime manifold we perceive is not the actual base layer of reality. It is an effective, coarse-grained description that begins to shatter under high-energy conditions. To construct a working theory of quantum gravity, we must abandon the assumption of a continuous geometric fabric and search for the primitive, high-energy substrate that sits beneath it. The variable slice density, or VSD model, attempts to map this underlying substrate. It synthesizes the static block universe ontology of relativity with the many worlds interpretation of quantum mechanics. The model operates on the premise that gravity and relativistic effects are not dynamic forces mediated across time. Instead, gravity is a static, time-independent structural gradient within a four-dimensional manifold. The physical dynamics we experience, the pull of mass or the strict limits on velocity, are perceptions created by how an observer navigates through this entirely static architecture. By reframing kinematic motion as structural navigation, the VSD model provides a heuristic bridge, linking the timeless nature of the relativistic block universe with the continuous splitting of the universal wave function. Zooming down to the Planck scale, the four-dimensional manifold is constructed from discrete elements known as configuration vertices. These vertices exist in a relativistic Hilbert space. A Hilbert space is a mathematical concept of a linear vector space used in quantum mechanics to describe all possible states of a system. In this model, each vertex represents a specific three-dimensional space geometry and its exact matter content. Here, the VSD framework reinterprets the Born rule. Rather than calculating the probability of a particle's position, the square of the wave functional amplitude represents the actual physical density of these coexisting three-dimensional geometric planes. This creates a counting measure for many worlds branches, removing the need for wave collapse. All outcomes exist as discrete slices. Mass isn't a pull, it's a structural source of bunching. Mass energy causes these slices to rapidly compress laterally, increasing local density. Because these vertices are discrete, the manifold remains finite. The slices compact tightly, but they cannot overlap infinitely, which provides a natural mathematical resolution to the singularities that break black hole models. Mass does not warp a flexible spacetime fabric. It increases the local concentration of discrete geometric slices within the static block. Reconciling this static block with the passage of time requires addressing diffeomorphism invariance, the principle in general relativity that spacetime lacks a preferred objective time parameter. To establish a temporal structure, the VSD model relies on the lapse function. The lapse function is a mathematical tool that determines the rate at which proper, subjective time flows relative to the universe's coordinate time. The core mechanical equation of the VSD framework dictates that this lapse function is inversely proportional to the slice density. Let's represent an observer's world line as an informational reading head passing through these vertical three-dimensional slices. As it approaches a massive object, it hits a region of structural bunching. The high density of vertices drastically slows its forward progress. The observer operates on a fixed experiential budget. Processing a set amount of updates per moment stretches their subjective experience across tightly bunched slices. Gravitational time dilation is not the bending of a temporal dimension. It is the mechanical delay of a conscious observer processing denser packets of configuration information. If mass governs density, we must examine how an observer's velocity impacts their trajectory through the preferred geometric axes of the universe. Velocity introduces anticipatory splitting. High speeds tilt an object's world line, inducing a higher rate of state-space splitting ahead. This directional multiplicity causes length contraction, effectively elongating the spatial distance traversed per unit of subjective experience. This explains the universal speed limit. The speed of light isn't a kinematic barrier. It fully saturates the substrate's branching capacity. Objects cannot accelerate beyond light speed because no more geometric paths exist to split into. The speed of light is the absolute maximum bandwidth of the universe's capacity to branch. The challenge is reconciling this highly discrete, constantly branching quantum reality with the smooth, continuous observations of modern astronomy. The VSD model uses a hydrodynamic coarse-graining procedure. This is a mathematical method for grouping distinct quantum configurations into clusters and averaging out their internal degrees of freedom. This interpolation relies on the functional renormalization group equation. This non-perturbative tool bridges the gap between bare, discrete mechanics at the smallest scales and the smooth space-time geometry we measure at the largest astronomical scales. At astronomical scales, the sharp, discrete fluctuations in slice density naturally average out. The jagged edges of the quantum vortices disappear. The resulting space-time geometry behaves exactly like hydrodynamic fields in condensed matter systems, where trillions of chaotic, interacting atoms present as a single, smooth fluid. The smooth, continuous metric of general relativity is not a fundamental law. It is a low-resolution, coarse-grained descriptor of a discrete informational field. When we apply the VSD framework at the cosmological scale, it provides immediate structural explanations for astronomy's most stubborn anomalies. Consider dark matter. Under the VSD model, dark matter is the gravitational footprint of disconnected branches, or dissociated geometries, that have split off from our local reality. While these parallel branches do not interact with our visible universe through electromagnetic forces, they occupy the exact same four-dimensional coordinate volume. Their mere presence mechanically increases the local slice density. This bunching perfectly mimics the extra gravitational mass required to explain anomalous galactic rotation curves. The model also addresses the Hubble tension, the ongoing statistical disagreement between local measurements of the universe's expansion rate and those derived from the early universe. Observers located in underdense cosmic voids measure a faster expansion rate because the matter there has much less gravitational binding, while observers in overdense galaxy clusters measure a slower rate. Look at this visual map of the cosmic microwave background. The varying expansion rates are driven by structural inhomogeneity in the branching web, mapping directly to the localized informational distances shown by the red and blue temperature fluctuations. Dark matter and the Hubble tension are not missing particles or broken measurements. They are the observable structural signatures of unseen branches sharing our coordinate space. This leaves the ultimate question. If the four-dimensional block is entirely static, how does a conscious observer experience the uninterrupted flow of time? Since the 4D block is a static collection of states, subjective experience is defined by the specific sequence of updates an observer processes along their world line. This is the reading head we discussed earlier, a physical system threading through the pre-existing density structure and decoding the states in sequence. The arrow of time is defined by the structural asymmetry in the branching density. The Big Bang represents a boundary of minimal dissociation. Because unitary quantum evolution naturally multiplies configurations, the perceived future is simply the direction of higher branch multiplicity extending outward from that origin. The variable slice density model aligns Einstein's geometric descriptions with the discrete logic of quantum multiplicity. Within this framework, physical force is the static relationship encoded in the global profile of slice density. The four-dimensional universe we perceive is not an empty stage where dynamic forces play out. It is an emergent, infinitely branched informational substrate.